Hey guys, so I'm going to talk about the mean value theorem, and basically this picture shows really what it is. I'll explain it later. but so basically in order to apply the mean value theorem, you have to meet these two conditions. Those conditions being, hold on here, right. Those conditions being that f of x must be continuous on the closed interval a to b and differentiable on the open interval a to b. And if you can verify those two conditions, then it's absolutely true that there exists at least one point C in the open interval a to b where f prime of c equals f of b minus f of a over b minus a. Now this is a pretty good theorem to know for calculus because it will more than likely come up more than once on the AP, and it would behoove you to know how to identify it and apply it. So what the heck is this all saying? Well, basically it's saying that the derivative taken at the point C is going to equal the slope of the line connecting the endpoints on the function. Alright, so I'm going to draw the picture again. Let's say we have some interval with one endpoint A, the other endpoint B, and so we know that our function has to be continuous. So it might look like something like this, but likewise also it looking like this is also continuous. However, our second condition says that the function has to be differentiable on the open interval. So functions that look like this are not differentiable at these points, these jagged edges here, or a more technical term that Mr. Sherman uses, pokey pokey ouch ouch. So you can't differentiate this type of function at the pokey pokey ouch ouches. So we're going to have to assume that our function is smooth. So I'm just going to draw a generic function that is continuous and differentiable over the interval a to b. So just say it does something like this. So on the graph, if this is the x coordinate A, then this y coordinate here, or the point here would be, what's going on with my pen here? A comma f of A, and right here B, at the x coordinate B, the point would be B comma f of B. Now if you make a line connecting the endpoints, that's what I'll try to do here. Then the slope of that line is just a change in y over the change in x, like we learned like 20 years ago. So the change in y would be generically here like f of b minus f of a over change in x. It would be b minus a. So again, that's just sort of the conclusion of the mean value theorem. And the idea really is if you look at the slope of the line connecting the endpoints, it looks like there would be a point, or perhaps many points, where if you drew a tangent line, the slope would be equal. So maybe here and here, sort of make tangent lines. So it appears that it has sort of the same slope. So I'll label these points for x coordinates, maybe C1 and C2. And so it looks like if you it looks like f prime of C sub 1 and f prime of C2, it looks like if you took the derivative at those points, then it would be equal to the slope of the line connecting the endpoints. Now, I know it's a bad diagram, but bear with me here. So again, the mean values theorem says that there exists at least one point, which there is at least one, whose derivatives will equal the slope of the line connecting the endpoints. So we're going to do an example here. Let's say we have the function f of x equals 1 plus the cube root of x minus 1. And we're going to look at it over the interval, let's say 2 to 9. And so in the problem will say find all c values guaranteed by the mean value theorem. I don't know if I spelled that right. Guaranteed by mean value theorem. Okay, so notice here that notice here that 2 is going to be our a value and 9 is going to be our b value. So what we're going to have is there's going to be some f prime of c, or maybe more than one, that equals f of 9, or f of b, minus f of 2, or f of a, over 9 minus 2. Now, we really do have to verify that the function meets the two conditions that I discussed earlier to make sure that we can apply the mean value theorem, or else you're going to be doing a bunch of work that you don't really need to do if it does not apply. So, looking at this function here, we know that under a cube root, because that'll be most likely where problems arise in the domain, but under a cube root, you can take the cube root of either a positive or a negative number. So it doesn't really matter what you have here under cube root for x, and you're just adding 1, which is inconsequential. So this function is continuous over the interval 2 to 9, and its domain would be all reals. Now, so to make sure that it's differentiable, I think the easiest way is to just take the derivative and find the domain of that. Just to make sure that the derivative exists at all points in the interval. So let's put a check mark on the domain. We verified that, and now we're gonna make sure that this function is differentiable in the interval. I've rewritten the function as 1 plus x minus 1 to the 1/3 power. So taking the derivative of that, we get that the derivative of a constant is 0. So we go 0 plus. Now, with this, we're gonna do a little bit of product rule mixed with a little chain rule. Yes, chain rule. And so we're going to move the 1/3 out front. So 1/3 times, leave the inside alone, x minus 1. Subtract 1 from the exponent here, so I'm going to get negative 2/3. And multiply by the derivative of the inside, which is just 1 here. Now we can rewrite this actually as 1 over 3 times the cube root of x minus 1 squared. Okay, so we need to verify that the function is differentiable in the interval that we're given. And if we find any points in the derivative that make it undefined, which are in the interval, then we know that the mean value theorem does not apply. So what we need to do is take a look at our function here. Make sure everything lines up. I'm sorry, excuse me. Take a look at our derivative here. And the only thing that would make this particular derivative undefined is when the denominator equals 0. Now, so if we have 0 under the squared here, 0 squared is 0. The cube root of 0 is 0, and 0 times 3 is 0. So we need to find, so basically x minus 1 equals 0, and solving for x we get that the derivative will be undefined when x equals 1. So we see that x equals 1 is not in our interval here. So the mean value theorem does apply because 1 is the only value that would make this function not differentiable. Okay, so I've sort of rewritten the problem here now that we've verified that the mean value theorem does apply to this function. And so we need to find the value which we're going to set equal to our derivative that the mean value theorem guarantees. So we have it all written out here. Now we just need to find the value. Obviously, on the bottom, which is going to be 7, 9 minus 2 is 7. And for the top, we get f of 9, so let's plug in 9 to our function here. So we get 9 minus 1 is 8, the cube root of 8 is 2, and 1 plus 2 is 3. So we're going to write 3 right here. And subtracting from that, f of 2, so let's plug in 2 to our function. We get 2 minus 1 is 1, the cube root of 1 is 1, and 1 plus 1 is 2, so we get 3 minus 2. So the value here that f prime of c is going to equal is going to be 1/7. So now we set our derivative equal to 1/7, which I wrote over here. So, okay, so we're going to get 1/7 equals our derivative 1 over 3 times the cube root of x minus 1 squared. Now you can replace the x's with c's, but it's all really the same. Okay, so we're going to solve for x here. Now it does look like a doozy, sort of, but it's always good to practice your algebra because YOLO, right? Anyways, so to find x, what I'm going to do here is multiply both sides by 3, so we're going to get 3/7 equals 1 over the cube root of x minus 1 squared. Then I'm going to multiply both sides by we'll call it x minus 1 to the 2/3. We're going to multiply both sides by that. X minus 1 to 2/3. So on this side we're just going to get 1, on this side we're going to get this big ugly thing, but bear with me. X minus 1 to the 2/3 times 3/7 equals 1. Alright, and at this point, let's just multiply both sides by 7/3, so we're going to get x minus 1 to the 2/3. This side, the 3/7 is going to go away. We're going to get equals 7/3. And to get rid of that ugly 2/3 exponent, we can raise both sides to the 3/2 power. So what that's going to do is get rid of the exponent on the left side here, so we're just going to get x minus 1. And we're going to get 7 over 3 to the 3/2 power. Okay, so I'm going to move the work up here. Just look up here for a second. And what this, we can rewrite this as x minus 1 equals the square root of 7/3 cubed. And so when it's the square root, we're going to get a plus minus value. So I'm going to add 1 to both sides to get x equals. And it's going to be 1 plus or minus this whole thing here, the square root of 7/3 squared. Okay, so now if we look at the interval that we're given here, 2 to 9, then we have 1 minus this whole thing here. Well, 1 minus anything is going to give us a number outside of our interval, so we can just go ahead and cross off the 1 minus, so it's going to be x equals 1 plus the square root of 7/3 cubed. And so this will be the c value, or x value. This will be the c value, where if you take the derivative at that point, it will equal the slope of the line connecting the endpoints. So I've calculated this value to be about approximately, my friggin' pen, approximately 4.56. So we've verified that the function f of x meets the two conditions that it must be in order to apply the mean value theorem, and we found the value of c that's in our interval that we're given, 2 to 9. So as far as I can tell, we haven't messed up here, so there's your mean value theorem.